project, I wanted to try to model what I do in practicality, which is electrochemistry. And so our molecule that we work with typically as a sensor is a little bit robust, so I wanted to try something a little bit simpler. So I started with a 1,4-benzoquinone, so very simple molecules. Should be something very easy to model, hopefully. So just to give you a little bit of background about what I do, this is an electrochemical cell setup, and you guys will get to hear in my thesis defense very soon some more about electrochemistry. But this is our working electrode in black here. And so what we try to do is we have a molecule brought to the surface of the working electrode, and we reduce and oxidize at that specific position. And so what I was trying to do was model what it looks like when we have this 1,4-benzoquinone and we're actually applying a potential or a wave packet to this site. So I wasn't able to do the whole electrochemistry, but I was able to start it at least. So setting up our model, we were able to take some crystal data from 1,4-benzoquinone and actually model our wells. And so here we have 2 oxygen wells, and then in the middle we have carbon wells to try to mimic what this would look like. So the methods that we use, this slide I actually took from Bubba since he's not here today. I was able to still try to incorporate some of his presentations, and him and I did some things that were very similar in our projects. And so we both use the same Schrödinger equation, and so he presented this nice slide that I'm using since he's not here. And then in MATLAB it turned into this nice long code, which I know most of you are probably familiar with. Some things that differ between ours is actually very small. I'm modeling a quinone behavior and he was modeling a dielectric behavior. And if you look at the actual equations between the two, they are very similar except that he's dealing with a slope and I'm dealing with potential. And I have a few more barriers than he does in his. But we're able to actually use a lot of the similarities between the two research methods in order to apply this to 2 different systems. And so I use 2 different methods in order to be able to compare the results to each other of how well they fit. And so here's the 2 Hamiltonians and then what that looks like in the code that we use with the MATLAB software. So the first thing that I did is I used an electric field potential of 0.01 atomic units. So what we see here is we have our quinone with our oxygen and our carbon wells, and we see this wave packet. And it's trying to get over the barrier. And I've actually, as you guys are watching, I've actually posted what the results look like as well, where the green line is method 3 and the black one is using method 2. And so we're able to see that about 15% of the wave packet transfers. And so what we're modeling here is we actually have this right here is the surface of our electrode is the metal. And so we're trying to see how much of that wave packet can get across the barrier and be transferred. So with this electric field potential, we only saw about 15% transfer. In our next example, we increased it to 0.02, and we're able to see about 40% of the wave packet transfer. You kind of want to cheer them on. You're like, you can do it. You can get over that barrier. I know. And we did this subsequently for a few more. Actually, we have a lot more data too. We also did some negative potentials, but I didn't want to bore you guys with too many videos. And as you see, as we're increasing this electric field potential, the slope is actually starting to increase. And so as we have our quinone modeling from kind of more of a plane wave to more of a slope, it's making it easier and easier for that wave packet to be able to transfer across. So this one we got about 60% of the packet transferred. And with 0.04, we got about 90% of the packet to transfer. But it took almost 100 seconds. This is sped up a little bit so that you guys weren't sitting here for 2.5 minutes for each movie, so you're welcome. So we're starting to see a little bit of an over potential. Okay. And then quickly, this one again, we saw 90% transfer, but it happened a lot faster at only about 80 atomic units of time. since we're out of time, I'll go a little quicker here. So conclusions that we were able to reach, more is better, that it was quicker, more the wave packet was able to transfer, but then also we need to take into account, is more really better? When we're thinking about electrochemistry, if you apply too much of a potential, you may start to burn your solvent, and there's a supporting electrolyte to take into account as well. So there's other things that we should factor in if we're to further this research with modeling. So finally, I just want to thank Dr. Keelan and my classmates for helping me with this complex subject, and also for Stephanie for helping me with MATLAB code and my references. Thank you.
Yeah, that's fantastic. Questions are very welcome. Yeah.
So, you mentioned one for Benzoquinone. Why this compound is, why you study this compound? And what is the derivatives of the Weatherman?
In our group, we base a lot of our research off of an anthraquinone. Close enough. Right here in the middle is very similar to one of our benzoquinone. So I wasn't able to take this whole model into account, so I took a part of it. This, and also in my research, this is where a lot of the reaction is taking place as I'm doing my electrochemistry, first here and then here. And so this is a main component of some of the things that I'm interested in.
Okay, more questions?
So what is this wave packet being transferred to? You talk about transfer, but it wasn't clear to me what physically this barrier corresponds to.
Sure, thank you for asking that. That's a really good question. So we actually have a potential electric field coming from a potentiostat down our working electrode, and it's the potential is being held right here and applied, and so we're trying to see how much is getting across that molecule. So take this and take it tiny and multiply it by the number of molecules that's at that surface, depending on the concentration.
Okay, so because I can't see the horizontal axis to that, so is that what is that horizontal axis?
This is X naught. It's our initial positions. It takes into account the ionization energy of carbons and oxygens to help determine what those well values are going to look like. And we've offset that the molecule to an exact position where the molecule is touching the working electrode without actually overlapping it too much, because you have to have the molecule come into contact with the working electrode in order for it to be able to transfer potential. Does that answer your question, Dr. May?
I think so, yeah.
Okay.
How do you again the molecule with respect to the surface? Was it optimized, or you choose a specific position?
It's not, it's all in solution, so they aren't, it's not a solid state at all. We do, in some of our research, where we believe that the internal oxygen is actually having the wave packet transferred first, and as you continue electrochemistry, then the second one goes too. But as far as orientation goes, there's nothing to determine which way it's orienting.
Okay, so you just chose one orientation in the structure.
Yes.
I have a question.
Yes.
So your electron going from electrode to your quinone, is it oxidation or reduction?
Reduction.
Okay. More questions?
I knew the answer to that one.
If you do the negative, it becomes oxidation.
Okay, let's thank Dasha for. And